Okay. Hi, everybody. Right now, we're going to be reviewing databases too. We're just going to cover concept by concept. There are some concepts that I won't cover, and I will explicitly state which ones I won't cover once we get to that section. Otherwise, I hope we have a good review. So first, we're going to start off with linear hashing. I was able to break down the notes into algorithm per se. So there are certain things that we need to do, and well, there's certain ways we need to know whether we should split or whether we shouldn't split during linear hashing. First, some key notes. I is the MSB. MSB is most significant bit, and we learned this in comp arc. And then N is the number of buckets. And now this is a simple hashing. If the number of buckets that are full is over the number of buckets total is greater than the load, then you must split. And if the overflow block is full, you must also split. And then when do you use an overflow block? If a bucket is full, but it's not surpassing the load, then you have to use an overflow. So let's get started with the practice. So using linear hashing with an overflow of 0.9, add these values. So at the very start, we have one single bucket, right? And it's with 0. And we relate it to the first addition, which is 0, 0, 0. So that's within the first bucket. Okay, in the second iteration, when you're adding 1, 0, 1, 0, well, you would first add it inside of this first bucket, right? Oh, well, it's ms is equal to 1. SB is equal to 1. So you'd have 0 and then 1. So at the first, it outlines to 0, 0. And then at the second, or the second most significant bit, it goes to 1. And as you see here, it is 1, 0, 1, 0. So it'd be here, right? Because the most significant bit in this case is 0. Okay. Least significant bit is 0. Exactly. And now we have the next addition. We're on this line. We're going to add 1, 1, 1, 1 into this linear hashing. Now, if you add 1, 1, 1, 1, you would do it in here because the least significant bit is 1. And now if we continue, we're going to add 1, 1, 0, 1. It would also go here. But if we check our previous algorithm, now the number of full buckets is now equal to 2. And the number of total buckets, our n, is equal to 2. And 2 over 2 is 1, which is greater than 0.9. So now we know we must need to split. So our MSB is plus 1. Let me just go back to the start. So we know our MSB is plus 1, so we do MSB plus 1, and now we have 2. That means we have a hash that goes 0, 0, 0, 1, and then 1, 0, and etc. So in 0, 0, we have 0, 0, 0, 0. And then when we create another hash, I'm just going to reorganize these values. So we have 1, 0, 1, 0. We just increase the space. Oh, yeah, sorry. More people walked in. Okay, there. Right here. Okay, we're just gonna expand these because I'm gonna need to write a lot of numbers here. So we have 0, 0, 0. What it was in our initial bucket is just gonna stay there. So we have, yeah, you're right. We have 1, 0, 1, 0. What is in this bucket? It's 0, 1. We have one value. It's gonna be 1, 1, 0, 1. And then what's in our Last bucket's going to be the same. So we have 1, 1. And in that we have 1, 1, 1, 1. Okay. Yeah. It adds the same. Exactly. Thank you. That's what I thought. Yeah, exactly. That's why we split. Okay, fair enough. 1, 1, 1, 1 is in there. So we don't display the last one. Okay, now when we add the second or the next, which is right here, it's 0, 0, 0, 1. When we add 0, 0, 0, 1, the last ending is 0, 1. Now we have to consider, okay, so we have 3 buckets. Our n is equal to 3. Right now we have 1 bucket that is full. Or 0.33, right? Or 0.66, whatever, 0.33. Since this is less than the load, we can't split. So we want to use an overflow to carry this value. So we're going to mark it with an overflow. Oh, God. Okay. Oh. Everything turned off.
Your thing turned off as well?
I don't think I'm sharing my screen anymore, which is weird. Well, yeah, my mouse is not. Yeah, exactly. True. Yo, guys. Okay. Oh, look at my.
Turn it off and then on again.
This is so scuffed. Okay, everybody in Zoom or in Discord, just give me 2 seconds. It's okay. I'm recording, but I'm not even sharing anymore. Okay, we're back. Oh, it's not on Zoom. It's on Discord. Uh, you haven't heard of it? Yeah, I think I might still have the QR code. Okay. So basically, for linear hashing, we add things in sequentially, which is why we still have 0, 1, and 1, 1 within the same spot. And I'm just going to write the overflow bucket, and I'm just going to add the next index to it.
Computer's still not on, Joey.
Wait, it's. Oh, God. Okay, guys, no more recording. Okay, this.
Well, I don't think the recording is the issue.
No, yeah.
Okay, there we go. It's back.
It's back?
Yeah.
Maybe okay.
The recording was the issue.
You think it was? Okay. It's
you can keep recording.
If I add it back and it changes, let me know. Okay, I'm sharing my screen.
Yeah, it's still on.
Okay. So we add an overflow. Why do we add an overflow? Well, because the number of full buckets does not exceed the load. And so we use an overflow. Now we consider, why is this right here 0, 1? And that's 1, 1. Because in linear hashing, we add things sequentially and we only shift the load from the bucket that is not like overloaded. So when we add in the next thing, which is 0, 0, 0, leaves us extra. Let's just add it anyways. 0, 0, 0, 0 would be in that position. And let's add 1, 1, 1, 1 again. When we add 1, 1, 1, 1, it would actually fill into this bucket right here. And now the overflow is now full. And as we stated before, when the overflow is full, we must split. Let me add another page. So I'm just going to rewrite what we have right now. We have 0, 0, 0, 1, 1, 0. We have, this is full, 0, 0, 0, 0. 1, 1, 0, 1. And then we have 1. And this is now filled. 1. Okay, the screen in the IEEE office is not working. Lucky for you guys. I think it's a connection. No, you're not, man. Okay, but now we have to split. And this one has 1, 0, 1, 1. So now MSB
It's currently off. Joe.
plus 1. Now it's at 4. Or it's at 3. Sorry. Now it's at 3. So now we have 0, 0, 0, 0, 0, 1, 0. Oh, sorry. MSB is increased by 1, and now we had to add our last index, which is 1, 1. So basically, as we progress, this is added in sequentially. So now when we reorganize, we have to do 0, 0, 0, 1, 1, 0, 1, 1. 0, 0, 0, 0, 0. Through here, we have now 1, 1, 0, 1. And then we have 0, 0, 0, 1. And then we take these two ones and we stuff it into here. I don't know where that came from. Then here was 1, 0, 1. Is it? Yeah. Okay. Yeah. Fair enough. And that's pretty much it. So, okay, just to reiterate, because that was everything cut off. We have some conditions for splitting. If the overflow is greater than the load that it can bear, so if it's less than 1, it will probably always, you would always need to split if it's full. And then if the overflow block is full. As we go through this database, we're adding to this value sequentially. So at first, you have 0 and 1. And then as you continue going, 0, 1. If you need to split, you would have 0, 0, 0, 1, 1, 0. And then if you need to split again, you would have 0, 0, 0, 1, 1, 0, 1, 1. When would you use an overflow? If you have a full bucket and you have a value that needs to be in that bucket, but you don't have the conditions to actually split that are stated above. And that is when you would use an overflow. So in this case, we had to add 1, 1, 1, 1. And we didn't have a condition that we needed to split. So then we used an overflow here to help carry that value. Okay, time to go into something way easier. Extendable hashing. Okay, basic algorithm for extendable hashing. You take the modulus of the value, then you convert it into binary and you fit it into a bucket. If the number in the bucket is greater than the records, MSB plus 1. It's kind of the same thing as linear hashing, but it's so much easier to grasp because they give you all the information.
Joey, can I interrupt you for a moment? You're not sharing your screen anymore in Discord.
Oh my, okay. Hey guys, my bad.
The database is ASMR.
Oh, rip.
Now I think we fixed
Okay, now we're on to extendable hashing, which is so much easier, guys. I'll just touch on what I said above. For linear hashing, as your need to split increases, you go from 1, 0, 1, and then you increase your split. And then it's 0, 0, 0, 1, 1, 0. And then if you increase and you need to split one more time, it's 0, 0, 0, 1, 1, 0, and then 1, 1. So it just exponentially gets bigger. Like linearly gets bigger. Okay, and that was pretty much it. And then I saved for the conditions for when you wanted to overflow and when you want to split. Time to go to extendable hashing. Okay, within the extendable hashing, there's a very simple algorithm that you must use. First, you take the modulus of a value. Then you convert whatever you get to binary, and you fit that into a bucket. If the number in the bucket is greater than the amount of records that are allowed, you do MSB plus 1. So using an extendable thingy or array, write the structure X mod whatever. Each bucket can hold 4 indexes. So this is a problem. I was about to ask, like, okay, what should I mod everything by? Give me a number. 5? Okay, perfect. So let's go. We have 2, right? 2 mod 5 is 2. 2 in binary is 0, 1, 0. Let's go 7. 7 mod 5 is 3, I'm pretty sure. Right. And then it's 1, 0, 1. Oh no, this is 1, 0. 7 mods. Oh yeah, it's 2 as well. Thank you. 2, then it's 0, 1, 0. Then we have 3 mod 5. It's 3. Then we have 1, 1, 0. And then we have 5 mod 11, or 11 mod 5, sorry. And that is 1. And that is 0, 0, 1. And we do that for all the values that are listed. But first we can start filling in our array. So right now we have MSB is equal to 1, or I is equal to 1, and we have 0, and we have 1. Or let's first start with 0, and let's break this into smaller steps. So right now we have 0. And as we can see here, this value, the first value that we want to add into this extendable hash is 0, 1, 0. So you're going to add 0, 1, 0 here. Okay, now we have the next value. The next value is 0, 1, 0. You're also going to add 0, 1, 0 here. Next value, it's 0, 1, 1. You're extending it to 1. And you're adding 0, 1, 1 to that. And then you have 0, 0, 0, 1, and then it also belongs there. And then we can continue with our modulus. Right now, each bucket can hold 4 values, so we're completely fine. So let's go 17 mod 7, or mod 5. That's the same thing. Yeah, it's 2, which is now 0, 1, 0. Okay, when we add this into our modulus, it will still point to 0, 1, 0. And instead of 0, 1, 0, I have to add the actual values here. My bad. So it's 2, no, it's 2, 7, 17. And then here is 3 and 1. So now we have 20 mod 5. And that is also equal to 0. So we have 0, 0, 0. Now we have 20. And our bucket can hold 4. So we're still good. When we have 22, 22 mod 5. It's 2, which is 0, 1, 0. Okay, now we have to add 22 to here. But that is now over the number that our bucket can hold. So we just increase what the indexes by 1. So plus 1. And now we have to store it into 0, 0, 0, 1, 1, 0, 1, 1. So we can use the values that we listed before and easily sort them. We have, in this one, we have 2, 7, 17, 22. This one we have now 20 that I can see. 1, 0 would have, oh, my bad. I think my Mac's like fussing up because it has so many things connected to it. For 1, 0, you have, oh wait, 0, 1. So let me just change these quickly because that's what I mistaked it by. This is 1, 0. This is 0, 1. For 0, 1, we have 11, and that is all. And then for 1, 1, we have only one value, which is 3. Okay, we have to add, oh, I realize here that it's also, no, this is still 4, and it's not greater than 4, so it's good. So now we continue. We have 22, we have 14, and 9 to do. So we're going to do it here. 14 mod 5 is 4, which is now 1, 0, 0. And then 9 mod 5 is 3, which is 0, 1, 1. Oh, it's 4, sorry. One, zero, zero. That's 4. So now we have to add, well, if it's 1, 0, 0, we're just considering 0, 0. It's 4, and then it's 14. 9, sorry, 9. Yep. 9 and 14, and that's it. We're done. And that was all of our values in a linear hash. There are more examples of this in the additional practices for all topics. And I highly advise you guys to study this because it goes over overflow, it goes over extendable hashing, and what to do in each case. Okay. Now we're just going to continue. We're on to B plus trees. I found this nice meme. I'm totally not a B plus tree enjoyer. I think they're disconnected again. Oh my lord. This is lovely. Okay, so some tips. N is equal to a value. They will provide you n on a exam. N minus 1 is the values that are allowed in a box, and you can have n children. And this all makes sense because if you consider it, let's say n is 4, and you can have n minus 1 values in a box. Well, you have A, B, and C. You can, of course, have 4 children. That can be less than A, greater than or equal, or less than B, and then the rest. The minimum element, it's 2 for 5 and 1 for n equals 4. How do we know this value? It's through this equation, which is the ceiling of n divided by 2 minus 1. So if you do ceiling of 5 over 2, that's 3.5 or 2.5. Now it's 3. 3 minus 1 is 2. So now we're going to insert 31. I'm going through a couple of these examples, or let's just insert 32 because 31 is already there. 35, sure. I'm going through a couple of examples. There's a lot more examples in those PowerPoint slides, but these are just the basics. So when you insert 35, you see here n is 4. That means you can have at least 3 elements inside each box. So you can just easily insert 35 here. Okay, let's keep going. Now we're going to insert 5 or insert 7. Okay. You see here, we're going to insert 7. 7 usually will be right here. But since n is still equal to 4, this should be oversized. So now we have to do a lot of swapping. Basically, you take 7, 3, and 5. Let me just push this actually to the other side. You have 3, 5, and 7. And then you also have 30. This would be 7, 11, 30. Wait. Push the wrong index, sorry. So by fitting in 7 through here, you're going to bring up 11 and then also put 11 down here because usually the values in the leaves are found, or the values in the upper nodes are found in the leaves towards the greater than sign. So 11 would be pushed up right here. And then this would remain the same. So it's going to be 30 and 31. And 11's value would be right here. Yeah. Oh, no, it's a different tree. But you're right. Okay. There's more, sorry. I'll just say there's more examples of this in the slides. So if I go here, and if you go through these slides, so right here, you see when they insert 7, they branch it apart and they push 11 up, or 7 up in this case. And then if you see, like, they have so many examples of being inserted, deleted, and it's also like your assignment had covered this as well. Okay. So one more important addition is a new root. So if you take this example and you're going to insert 50, you see that 50 would be here. But since n is equal to 4 in this case, it couldn't fit. So basically what you would do is you will break it apart. I have no space. I'm just going to take a screenshot of this. Oh, great. Sorry, be patient. I'm just, okay, there we go. So all you'd have to do if you're going to insert 50 is take this. This side becomes the same. This remains the same. The only thing that changes is down this half. So you have 10 and you have 20. And these would point to the same boxes. But since you're pushing 50 here, you have to also fit it into this side. This would become a new box. And 40 would go up to a new root. And 30 would also slide over and become a new root as well. So what would this look like? Well, you have 10, 20, you have 30, 40. 30 would map to the same things. What is less than 30? It's going to be 20, or sorry. It's going to be 20, 25. What's in the middle? It's going to be 30, which is the same value here, and 20, 32. And then what maps higher is going to be 40, and then 50. And then this, we just rewrite the whole thing. I have to move 20. Just give me a second. Let me just double check. That's not this. They started on the wrong side. What do you think? Did I start it on the wrong side or up? It's not on delete. It's on addition. Okay, yes. Okay, okay. That's probably it. Okay, sorry. No, no, because you have to actually move 30 up. So it'd be 10, 20, and then 40. What's less than 40 would be 30, 32. What's greater is 40. Yeah, 50. And then 30 which doesn't fit anymore, would have to be pushed up. So right here, 30, you have 20, and then it would be the same thing, 20 and 25. And this would be the same. Okay, why did this happen? Let me just delete this a little. When you're adding 50 to this bucket, you see that it cannot fit because n is equal to 4. So when you add 50 there, you'd have to create a new root. Why you choose 40? 40 is the median of this bucket. The median gets pushed up into a new bucket. Or well, it gets pushed up into the original bucket to make space. So 40 gets pushed here. Then you find the median of this bucket because this is also overfilled. The median of this bucket is 30, and 30 gets pushed up to a new node. Does that make sense? Let me check the chat. She forgot to share a screen. Oh, sorry, guys. Okay. So that's just another important example. I talked with the professor after class, and this is kind of her notes. Oh, where's my bag? It should be there. Thank you. I'll tell you what she detailed out to me. She basically said to review that slide, know how to insert new root, know how to delete elements from it. Anything that is too difficult, she won't really put on the exam. She'll put on only intermediate stuff. Anything that you've done in your assignments probably won't be on to the same intensity unless it is very simple. So keep that in mind. Okay. When we delete 50, let me just get a new color. So when you delete 50 from this, n is now 5. If n is 5, we have a calculation for min elements. Min elements is equal to 2. Oh no.
Okay.
Yeah.
If you touch that thing. Let's try not to touch that.
Okay, I'll try that too. So let's delete 50. Okay, when you delete 50, you can't really do that because then the min elements is 2 and it's less than the min element. So what do you have to do? Well, we're going to need to consolidate. How do you do that? Let's move. Let's combine these two. Right? And then you just push this one down. So basically it would now be 10, 40. This would be the same. This would be the same. This one would be 40, 100, and 120. Pretty sure that is it. Correct me if you think. Okay, yeah. So how do I find this minimum element? There's a nice equation. It's ceiling n over 2 minus 1. So 5 over 2 is 2.5. Ceiling, so it's now 3. 3 minus 1 is 2. So the minimum element for this is 2. And yeah, pretty much it's a combination of AVL trees or 2-4 trees that you've learned before. There are some nuanced rules. In an AVL tree, what is usually like in a root node wouldn't commonly be found in the leaf, but for a B plus tree, it is usually the case. Okay, so let's delete 50 from this. Now, if you delete 50, you see that the minimum element is still very small. And you have to condense and probably split. So now we have 10, we have 40. 40 can remain the same. 40 second. Let me think this through. Okay, we have 10 that has stuff there, 20, 30. So 40, instead of keeping 40 here, we're going to actually push it down and take the median from here, or take this value and push it up. So we're going to have 35. This is going to have values. This corresponds to this. Here we have 10, 20, and 30. And then in this bucket, we're going to have 35 and then 40. Why did we choose 35 to push up? Well, we have 10 here, we have 20 here, we have 30 here, and we have 35. We wouldn't push 30 up because that would mean 35 is out of place. And you can't really have that happen. So 35 would go up in place of 50. And then 40 would actually get pushed down and over to the side. Okay. Just once again, it's very illustrated. She probably won't ask you to explain your steps in the problems. She'll just give you a bunch of numbers and say perform a B plus tree. Is it okay? Thank you. Do linear hashing with this values. As good practice, destroy a tree and then remake it. So some drunk drawer stuff. It's down?
Yeah.
Oh my lord.
Okay.
Oh, let's go. Okay. Junk drawer, find the record with key is 29. So if they ask you to search through to find a key, you have 19. Is it down again? Oh my lord. 19. Okay, it's back. Okay, so they might ask you trace the path to find a record with the key 29. You have 19. It's greater than well, 29 is greater than 19. So you to go to the side. Now we have the key, which is 29, and you'd have to just go to the max and then find 29 here. They probably won't ask you to really trace it out. But if they tell you what are the values like found in that path, 19, 29, and then 29. Now they're going to ask you find the values from 5 to 17 inclusive. How would you do this? Well, we have 19 here. We're going to the side. We have 5. Okay, so it's 5. And trace it down. We have 5. We have 7. 5. Where's my key? We have 5. We have 7. And then we keep going. 11 and then 17. So that is just some nuanced questions. There's a lot more examples in the notes. So some formulas to know. It sucks that we don't have a formula sheet, but if you can remember some of these, it's very important. The number of leaves are equal to the records over keys. The number of blocks in each level are equal to leaves over keys plus 1. And you're going to do this recursively until you end up with the value of 2, because that's when you know like the roots of the tree is 1, right? When you have a value of 2, you know the root has 1 block. So some examples of this. Assume a relation has 100 records and a B plus tree. There are 14 keys per index blocks. How many leaf blocks does an index have? So we're trying to find the number of leaves. Well, what did we say before? Number of leaf is records over keys. So we do number of leaves or over records, which is 100, over leaves. And this is ceiling. So you're going to round up, which makes sense because you cannot have half a leaf. Okay, we continue. You have an index of 83 leaves and 6 keys. How many levels does the tree have? Okay, so we do the first calculation, or the second, we use the second formula. which is number of blocks in level is equal to leaves divided by keys plus 1. So we have number of blocks is equal to leaves, ceiling, keys plus 1. So in this case, it's going to be 83 leaves over 7.
Excuse me.
Yeah,
That's a question.
sure.
Just in the previous example,
Yep.
you said that the number of leaves is equal to 1,000 divided by the number of leaves.
Oh, it's 14. It's the number of keys. The formula is right there. Okay. So in this case, it is 12. Sorry, I can't find my thing. So we have 12. Okay. Now we're going to do this process over and over again until we get a value of 2. So we have number of blocks is equal to, it's going to be 12 divided by 7, which is going to be 2. And that's it. So we know if you wanted to count the number of blocks or the number of nodes, it would be 1 plus 2 plus 12 plus 83. But since they just asked how many levels, it's 1, 2, 3, 4. Alrighty. So the file and storage management, I asked the professor and she said, if you just read the slides, you'll be fine. Or if you want to know every question and know this stuff in detail, read the chapter. But I asked her again and she's like, okay, the slides give you everything you need. There are some formulas for this chapter relating to like find the max rotation delay, what is the transfer rate. And my suggestion is look at the units because they usually tell a lot in terms of these questions. So transfer rate, you know, okay, you're transferring stuff, you're transferring information over time. So information in these types of things are stored in bytes or bits or megabytes. And it's going to be over time. So you know it's going to be per minute. So if they ask you a question, it's going to be, you're trying to get this unit of measurement. So above here, consider a disk with sector size 512 bytes, 100 sectors per track, giving the rotational speed of this many revolutions. What is the maximum rotational delay? Rotational delay. Well, rotational delay is 1 over the revs per minute, which means it's 1 over 720, 7,200. Okay, assuming that 1 track of data can be transferred per revolution, so we know it's 1 track per rev. What is the transfer rate? So transfer rate, can I just find my thing? Transfer rate is equal to, okay, let's see what the units they gave us. They gave us 512 bytes. And they say it's consider a disk of the sector size. So this is how many bytes per sector. And we have 100 sectors per track. And we know that from this right here, 1 track per revolution. So we have the revolution, which is 720. And we know that we have 1 track per revolution. So really, and this is sector per track. So the speed of this whole thing would be this multiplication. Because we have bytes over sectors. We have sector over track. And then we have 17 revolutions per minute, right? So times this track. pararev. And then if you cancel out your units, you have sector, you have track with track, and you have revolutions per revolutions, you end up with bytes per minute. So it's just a matter of looking at what's giving you, actually reading the question and trying to find the units of measurement you need. Alrighty. Now we're on to normalization.
Sorry, I have one question about the above
Sure.
example. It says 100 sectors per track. Are there not more sectors on the outside of the track than on the outside of a disk than on the inner tracks?
So when track of data can be transferred per revolution, what is the transfer rate? I think they're just considering. I don't think this is like an application question per se. Like you are like doing application with it, but I don't think they want you to consider like the full disk, if that makes sense.
Okay.
Oh, the screen's dead.
No.
Okay. Yeah. Yeah. Okay. Now we're on to normalization. Normalization is really easy if you break it down into steps. I went ahead and took this chapter and broke it down into like its individual parts right here, which has some rules that are very useful. So I'm just going to pull these rules up. And I will split my screen. Let's just zoom out. Man, when technology does not listen to you. Okay, but let's just go. There are some rules I pointed out when I use it. So show that all attributes of R are functionally dependent on each of the attributes. What does functionally dependent mean? Well, it basically means everything can be generated from that attribute. So in this case, we're using A. We know A generates B, C. From the rules, we know that A generates B and A generates C. So right now we have A. Within it, we can generate B and C. Okay, we know that B generates D. Since A generates B, we can assume that A also generates B. Or D, sorry. What else? Yeah. So we have A generates C and A generates D and CB generates E. So we know that A generates E. And we have E generates A and A generates E. So the logical conclusion is that A generates A. Yeah. And this is all in the rules. I'll probably paste these rules in these notes. And these rules are located on your slides. So it's using transitivity, reflexivity, positivity, right here. And the teacher actually details them out really well in the slides. And I'm just teaching you application of them. I added a special rule that is highlighted that was used in this case. There's a big proof on C, D generating a value. And then if A generates both C and then A generates D, it being able to generate the same value. But you can just know it as just a finalized rule. I don't think she wants you to truly explain what is going on. So once you're doing C and or B and C, I'll do it in a different color so it's distinguishable. Let's go red. So we know that we have B and we have C, right? We know that B generates D. So if B generates D, we can have C if B generates D and CD generates E, well, we can have CB generates B or E. And if E generates A, then we can also assume that CB generates A. And since CB generates A, and we already proved that A is FD, that means CB is also FD. And that would be a viable enough proof, because if CB can generate A and A generates all other values, then CB also generates all other values. So yes. So when you're doing these proofs, feel free to like use the ones that you've previously done before. Okay, which FDs do not hold in this table? So you're going to come across this question. She says specifically in her announcement, she's going to give you a table and you have to determine if it's NF or like what functional dependencies hold, what don't. And these are just some tips to come back to that. So some key things. MK is multi-attributed primary key. If you have an MK generating an MK, so a multivariable or multi-attributed primary key generating another multi-attributed primary key, which is a subset of a primary key. Oh, okay. Here, if you have a subset of a primary key generating another subset of a primary key, it does not hold. It's very bad. You will see this in the table and it'll make a lot more sense. Actually, let's look at this table. So we have a question. What functional dependencies do not hold? We have C generating P. So if you look at C right here, can I zoom in? I can't really see my mouse. Okay. So we have 100 here. That generates 10, right? And then 100 generates 20. So we have 100 generates 10, 100 generates 20. And then we have 200 generates 50. And then 200 also generates 20. As you can see, this one does not hold. Why? Because this multivariable attribute, like the values are different. So, okay, basically the left side, let's see, left side, if you have the values like 100 and 200, you're allowed to generate the same value. But if you have 100, you're not allowed to generate two different values using that. It's kind of difficult to explain, but dew points probably my... Okay, let's just focus on C and CNAME. So you have C, and then you have CNAME. And if you look at this, every time you have 100, you generate dew point. Every time you have 200, you generate Martin. Every time you have 300, you generate dew point. It's okay if these values are duplicated, as long as they end up with the same result. So C to CNAME is good. This is good. In this case, C to P, when you have 100, you generate 10. When you have 100, you generate 20. That's okay. When you have 200, you generate 50. When you have 200, you generate 20. That is bad. What? Yeah, and it's also bad up there. Pretty much every 100 needs to generate the same value. And this is wrong. And she'll probably always put a table with duplicates. So if you go the same and you compare P to type, you have 10. And where is type? Types are here. When you have 10, you have A32. When you have 20, you have B12. And then right here again, when you have 20, you also generate B12. 20, you have B12. So this is actually holds. Now let's do color to name. When color is black, you have a P name that are different. And when color is white, it has door. When it's black, it has something that is also different. Bumper, it is different. So this does not hold. So this does not hold. This does not hold. Let's do to S to quantity. When you have 30, you generate 25 and 30. So this already does not hold. So basically, left side generates right side. For every left side value, it's going to generate a single right side. And it's described up here. A subset of a primary key generates a subset of a primary key is bad. If you have a subset of a primary key and you don't have a unique value, then it's not unique for all tuples. There's a piece of text at the very bottom that actually illustrate this more. I can't find it. Right here. A relation, okay, skip the relation part. That's for 2NF, okay. That's pretty much, but this is correct. No, I have them here. So they might actually ask you to list some definitions during your midterm. So let's fill them in. You have a superset, and it's a subset where you can uniquely identify every element. So let me write that down. Uniquely ID every element from the table. A super key that does not have a smaller subset inside. That is also a super key. And then you have candidate key, which is user defined. Basically, a candidate key is, let's say you have a super key, which is like A and B. You can have a candidate key that is A. But if you have a candidate key that is like also like, or let's say, let's add another element here. A, B, C. You can have a candidate that is, or you can't have a candidate key that is A and B because it is subset of a super key. But you can have a candidate key that is, well, it has to be unique, basically. Let's just go here. So suppose that this is a primary key. And that the following FDs, functional dependencies, hold in CSP. Show that CSP is not in 2NF. What does 2NF mean? Non-element key fully dependent on primary key, not just a subset. So every non-element key must be fully dependent on a primary key. We have to show that this does not hold in order for it to not be in 2NF. So let's see. Okay. We have C name is applied on just C. By fully dependent, it means not just a subset. And C name is only dependent on a subset of this primary key. So it is not in 2NF. Depends on a subset. And then this is where the text comes out. Oh no, now it's lost its decomp. Yeah. But pretty much if you read this out, you can ignore, well, you should read out the first part, but primarily what's important is the second part. When you want to remove partially dependent attributes from a relation, you do so by placing them in a new relation with a copy of their determinant. So for this algorithm, I think I didn't write it down because I had it here. Okay, right there. When they ask you to give you a lossless decomposition of it, every left side that generates a right side is written together so we can avoid partially dependent keys. And if you have two left side elements, it is also written with your right side. And then if you have an element that is not found in the right side, you just have to take the whole primary key and then add that to it. So it's primary key plus right side. So in this case, I think I recopy it down below. Yeah, give a lossless composition. So in this case, you just follow this relation. This would be R, C prime, or C sharp, and then C name. Then it's R, P, and then P name. R, S, S name. So we're done these three. Now we have P name and type. So P name is related to it through P. And we have to make sure that the left side is a primary key. So for this case, we'd have to do R, P, P name, and type, I'm pretty sure. Okay. And then for P name and color, it's the same thing. You're going to do R. You could just actually just add it here. Name, type, and color. Now you have one with all of the with two left sides. You do the same thing, C, P, and then S. And then you see here, we did C name, we did P name, we did type, we did color, we did S name. We did dates. Actually, no, we didn't do date. And we also did not do quantity. And what did we say that we should do when things are not included in this list? We have to take the whole primary key and add those elements that are not found into a relation. So basically, our whole primary key is, if I can see it, thank you. It's R, C, P, date. You have to add quantity as well. Okay. Also, if you notice, which I forgot, we have P and P name, and then we also have P and P name into a relationship, and this is duplicated. Since it is duplicated, you're allowed to remove one of these relations. And that's it. That's a lossless decomposition. Okay, let's keep going. So you have some definitions here. It's basically the definitions that are on the sheets. So I'm just going to copy them down and then go through them. The best way to know some of these stuff, what is 1NF, what is 2NF, what is 3NF, is to try and write it in a way that you can understand clearly. And it's also in the slides. So 1NF, you have no atomic values. What does atomic values mean? Well, it means that you have no value that can be broken into two parts. So a key in of itself is not an atomic value. But let's say you have like a phone number. That would be atomic. Atomic value also means unique. Uh, so it's like it's a key composed of two values. You have a phone number. A phone number can be broken into like, well, a state number, which I think for Ottawa is like 163, and then the actual value. Then you have 2NF, where a non-key element fully depends on a primary key. This basically means that any subset, like your primary key should not be a subset of a super key. It has to be like the full key. So every right side is dependent on a primary key. If you have a unique element as a primary key, it is automatically 2NF. Thank you. Okay, now for 3NF, every key attribute depends on transitivity. So as in like if A is B, B is C, we have A to C. And what's not covered in here is BCNF. BCNF basically means that every left side must be a primary key. So now if we check with lossless decomp, which they might ask you to do, you know, if the intersection between the like R1 and R2 holds, that means equals some value, then it's lossless. Or like, sorry, if the intersection between R1 and R2 gives one of those values, then it is lossless. So you're just making sure that no relation is removed. So right now, I've listed here, we're not covering 3NF or BCNF, because if you cannot tell, we're on slide 16. I think we're good on time though. So SQL, there's a bunch of practice in the slides, and I'll also detail something that the professor told me. If you go to table content, you go down to relational algebra and calculus review. If you go through these questions and you actually write them out yourself, they start from very easy concepts to very difficult concepts. And it covers that for each one. So very simple SQL to very hard SQL, variational domain calculus to very hard domain calculus. She basically said that they go from easy to intermediate to hard. The hard won't be on the exam. She might take like the last half of intermediate and the last half of easy and put that on the exam. So like final or assignment questions won't be on there because she assumes that you're taking multiple days to do these assignment questions. But yeah, so if you find something too difficult in these slides, don't worry. Okay. And what's good practice is she might just give you one of these problems. She might give you a database and she might say like, okay, do this in SQL, do the same query in relational calculus, and do the same thing in domain calculus. Okay, but to start, so right now, I think this is domain calculus, or no, this is SQL. So find the boats reserved by Albert. So whenever you have a query like this, where the keys are only related to in a single database, you must join that database. So join. Oh, well, that's in actually relational calculus. But in this case, you're going to do something like select from, let's go S, B, and R, where, and then you have your query. What would your query be? Well, SID is equal to BID. And we're trying to relate it to R. Oh yeah, sorry. This is S dot and this is B dot because we're taking it from these tables.
Shouldn't it be S dot SID and then R dot
Yeah, yeah. Yes. Dot SID is equal to R dot SID, and then B dot bit ID is equal to R dot bit ID. And
Wait, why you said?
give me a second.
S dot SID.
Sorry.
Okay.
Yeah. Sorry. Let me just move this up. Yeah, select. Find the color of the boats. Yeah. Yeah, select color. You're exactly right. That's the part that I was missing. Okay, so select the value of the column that you want from the tables where these values. Basically, you want to make sure that this SID is the same as what's in S, and this bit ID is the same in what is in B. Now, if you're going to do the same thing in relational calculus, oh, and S name is equal to Albert. Sorry. Missed that. Okay. That's correct. But if you wanted to do this in relational calculus, you basically, you have to select, what are you selecting for? You're selecting the columns. So you're selecting, and we're going to join S and R, or S and B. So from S and B, you're going to select, I think you could do this in one.
Isn't it S name and then you say Albert and then you do the project?
Yeah.
Yeah.
Sorry. Can you say that again?
Isn't it project of?
Yeah, it would be.
Yeah, okay.
Project of, and then you're taking color, which is the value you want, is the select of S name is equal to Albert.
And then you just join.
Exactly. It's very S and B. I don't think we'd need it. Oh, true. And I think that'd be it. So basically, this is kind of what you want to, you're probably going to find. You're going to find something that is, she wants you to write it in SQL, and then she wants you to write it into relational calculus. So find all the sailor IDs that have a rating of at least 8 and that are reserved to boats. So for this one, you're going to use union. You're going to have the sailor IDs. So let's say select S dot I. Oh, SID. Okay. From, and I think this is S, where rating is greater than 8. Union with the select SID. R, sorry, thank you. No, you're good. R, where, and then boat ID is equal to 103. And that was it. If you're going to do the same thing in relational calculus, you're going to do here, you're going to find the sailor ID. So you're trying to find SID. You're combining these two tables together. So you're actually going to join S and R. Oh, we're going to do a union. That's true. We're going to select SI rating, yes. Rating that is greater than 8 from S. And we're going to union that with a select of BID. Oh yeah, true. 03. project is X, right? Okay, yes. Oh, yes, yes, yes. Yeah, I see. And then SID. Okay, and that was it. I feel like you can write it both ways. Okay. I wanted to kind of do like a small review of relational calculus, but it might just be better if I go through what I wrote down here. I basically went through all the slides and made notes on what every symbol meant. And like when it would be used. It's kind of blurry. You have select, you have project, you have union, you have set difference, you have product, you have p name. Basically, I'll probably give you this. It might be hard to zoom in, but it has everything. Project basically selects a column from a table. And I also give you details of when that would be used. Select takes a table and it selects from a requirement, so it queries a requirement from a table. So a condition. In here you have select the part name is equal to physics from instructor. So if you're going to select something, you could say department name equals physics from the table that is instructor. So this is going to be project. This is select. What else? You have set difference, you have union. There's one thing that I do want to go over with, if I can cancel that. And that is union, well, natural join. So how it's written in the slide, it's kind of complex, or it's kind of hard to understand what is going on. But I was able to break it down. It's either this one that I wanted to review or another one that I wrote out by hand, but I can't find it. So we're just going to go with this one. Let me just take this. Okay, for natural join. Natural join basically takes two tables and it tries to make you have to have a matching column from both tables. And from that column, it selects all the attributes that are similar. So in this example, they gave us a table, and within that table, you had A, B, C, D, and you have B, C, and E. And then you have different variables within it. So you have A, 1A, and then this has like A as well. This is B, 2Y, and then A, Y, 4, B, then B, and then one more. And then you have 5, 2, B, and then B. And then in the second table, you have 1, A, you have 3, A, B, and then you have 2, B, 6, sure, I can't really read that, and then 3, B, Z. Basically, since these two since when you do natural join, you're trying to compare which two columns are in common, you see that they both contain B. So when you naturally join these two tables, it's almost like a propagation. You go here. So you find wherever B is the same, and you write these values. So in this case, it would be A, B, C, D, E. So when B is 1, you have A, and then E. Right? Oh, sorry. And it's A for E too. Oh my. Let me just quickly do this. And then for B is 2, right here, you have B, 2, Y, A, and then E. Then you also have B to Y, B, and then 6. So you'd write these two indexes. Basically write everything that doesn't match. I'm probably not explaining it as well, but for B is equal to 3, it's not in the other column, so it is actually removed from the table. Let me just try zooming in here. Okay, you can't really see it because of all the fractures. That's kind of why I wanted to print it out. But every column matches to a certain index. You see B is 1 here, and then B is 1 here as well. And then B is also 1 below. And the D and E have different values. So A, 1, A, and then it has the values from the top. And then you have A1, and then it has the values from our bottom. And you have multiple joins. So you have joins that connect, joins that are just left, right join, and then outer join. And all these joins, the differences are just trying to preserve your table. And even like through preserving your table, you're introducing null values to your joins, pretty much. You might get a question on your exam that's like, what are the differences? Or like you have to know the differences between using an outer join versus a regular join. And then other than that, that's pretty much it. Some topics that I did not cover on this exam or like for this exam that are pretty important is BCNF, 3NF. Most of SQL, it's pretty much what's in these slides. If you could do this practice and you're comfortable with majority of them, even if you find a couple hard and difficult to think about, that's okay. They probably won't exist on your exam. You will be fine. For BCNF, I covered the initial concept of it, how left side has to be a primary key, but I did not cover decomposition, which is very important. And then for 3NF, you from a table, you should try to identify if it's 3NF. And you should also find out or learn about the conversion and a decomposition of it. Yeah. Let me just quickly read what the notes the teacher laid out for me. Okay. Orders. Okay, so you might have some questions asked. So you have functional dependencies, and you're gonna have basically what is the fundamental can't say the word anymore. What is the FD? Functional dependency of the table. What is the normal form? You're going to be given dependencies, and you might be asked to find F plus, right? For composed relations. This is basically what we've done before, but instead of labeling it as F plus, we just did the math directly. What else? For B plus tree, be familiar with inserting and deleting. What's deleting? We covered a little bit of those concepts here, but in the slides, there's a lot more examples. And then for linear and extendable hashing, be comfortable with ordering them, ordering indexes, and know how to insert. and overflow. And there's probably more at the front. No, that's pretty much it. Okay. That is all. That is all I had prepared. I will provide these notes on, well, on my server, and all of the notes that I've written for every chapter. So all of the synopsis also. Thank you guys so much. Thank you, Ben. You have questions?
I have a question.
Okay, okay.
As writing SQL with rows, do you think we might get like a question on the final, let's say, the answer for it will be left, natural, going
Yeah,
forward?
yeah. Okay, I guarantee you there'll probably be a question. Oh, the Zoom went off. Oh wait, stop the share. And then end this.